All right, so first section we're going to look at in the book is section 1.1, functions and graphs. Covers a lot of basic stuff that I know you've already seen before, so we're not going to spend a ton of time on it. But where we will slow down is when they get into graphing calculator stuff, because I'm sure a majority of you aren't familiar with like how to zoom or change a window on the calculator. And that's something we're going to do all year. So we'll go nice and slow through calculator stuff. All right, so the first thing is basically just kind of going through the types of numbers that we're going to be working with for quite a while. Starting with the simplest numbers, working up to the more complicated and more theoretical numbers. Counting numbers. Anybody tell me what are counting numbers? Like what do they start with and what do they kind of go up by? Think they know? How about Joe? Have any idea? Think about when you're going to count things. What do you start with?
1.
Yeah, you don't start with 0 when you count, right? You're going to count 1, 2, 3, 4. You start with 1. And when I just counted, did I have any fractions or decimals? Let me think. About Jacob? No. So counting numbers, I'm not going to write it down, but if you can't remember it, you might want to make a note. Counting numbers start at 1. They don't include fractions, decimals, or negative numbers. They go up by 1. Now, whole numbers are very similar, but they add one extra number. Does anybody know what extra number is included in whole numbers? And it's the only number that's different between whole and counting.
0.
0. It adds the number 0. So you can almost think of it as like when you go from counting to whole numbers, 0 has been invented. Well, doesn't 0 just always exist? It's a number? No, 0 didn't always exist. So basically the reason we have each number set is because there's certain calculations you can't do if you don't use more complex numbers. Let's look at addition. How about, Tori, can you give me a counting number? 3. Plus. And how about Gabe? Can you give me another counting number?
7.
7. If I add 3 plus 7, I get 10. How about, is it Kaya? Kaya, is 10 a counting number?
Yeah.
Sure, 10's a counting number. In fact, you could have given me any counting number plus any counting number, and the answer would always be a counting number. So addition works fine. Let's try subtraction. Let's do the same problem. Counting number, except I'm going to change plus to minus. 3 minus 7. We know what the answer is, but Emily, is the answer a counting number?
No.
No, it's not. So we can't do this calculation with counting numbers. So that's why we need to invent a type of number that would allow us to do it. In fact, we can't even do this calculation with counting numbers. You can't do 3 minus 3. If all you understand is counting numbers, the answer to this problem is undefined. So that's why we have whole numbers. Now, we can answer that question because the number 0 exists. But even with whole numbers, we can still run into some problems with arithmetic. And by problems, I mean take a whole number, take another whole number, do some operation with them, and the answer is not a whole number. Can anyone give me an example of a whole number, put an operation between them, and the answer is not a whole number? Yeah, Allison?
3 divided by 2.
3 divided by 2, that's a problem. All right, so division we can run into problems. What would be another example besides division? That is an example. Natalie?
Like square rooting.
Okay, square root, that's a problem. Let's stick to the 4 basic operations. How about add? If we add a whole number and a whole number, would we always get a whole number? What do you think? Yeah, adding is okay. How about subtracting? If we subtract a whole number from a whole number, but Robin, will we always get a whole number? All right, is 3 a whole number? Is 7 a whole number? What do you get if you do 3 minus 7? Negative. Is that a whole number? No. Whole numbers don't include negatives. They're basically like counting numbers, except they also have 0. So that's why we invent the next set of numbers, integers. Now we can answer that question. Okay. Without integers, we have to say what I just circled is undefined. Can't be done. Can't take away more than you have. It doesn't make sense. Okay. At least if you're talking about physical objects. Like if I have 3 pens in front of me and you want to take 5 of them, well, you can't. I don't have 5. I only have 3. So how can you take more than you have? Well, that starts getting a little more theoretical. So now we get into negative numbers, which you could think of as like being in debt, okay, or borrowing money, okay, things like that. But even with negatives now, so now we've got positives, we've got negatives, we've got 0. What numbers do we still not have with integers? Yeah.
Decimals.
We don't have decimals, we don't have fractions. So if you want to take like 3 divided by 2, 3 is an integer, 2 is an integer. Integer divided by integer, the answer is not an integer. So now we have to basically think about breaking things into pieces, parts, and that's what the rational numbers do. So rational numbers, we have fractions and decimals. Okay, so each number set that we invent just allows us to take calculations one step further. And for most everyday purposes, rationals is about as complicated as you need to get. Maybe you spend $20.37 at the store. Okay, so it's a fraction of a dollar. Or if you're getting gas, you might get a fractional amount. If you're cooking, you might need 2/3 of a cup of something. Okay? But again, for most everyday purposes, that's about as complicated as people get. Now, when we get into these other sets of numbers, we're getting more theoretical. Numbers that most people don't use in everyday life. Generally. Okay, some people do, but the average person, probably not. Okay? So, irrationals is the complement to rationals. So, if rationals, which I thought I wrote, no I didn't. If rational is anything that can be written as a fraction, irrationals are numbers that can't. Can anybody think of a number that you cannot write as a fraction? Yeah?
Does I count?
That's even more. We'll get to that in a little bit. I'll mention it briefly, but I'm not going to write anything down about that yet. But we'll talk about it. Yep, were you going to say something? No. Anybody give me a number that you can't write as a fraction? About Joe?
Pi.
Yeah, pi. At least we don't know how yet. There's no pattern. At least they've written pi out to millions and millions of digits, and there's no pattern. It doesn't repeat. If a number has a pattern to it, like say 0.33333, and it just keeps repeating, that's different. That you can write as a fraction, 1/3. But if there's no pattern, it doesn't repeat, you can't write it as a fraction. So pi is an example of an irrational number. And there's a whole other category, somebody mentioned it earlier. Other kind of numbers you can't write as fractions. Does anyone remember? Somebody said, we were talking, I said, well, let's stick with add, subtract, multiply, and divide for now. And I said, we'd come back to that operation. Yeah? Square roots. If you take the square root of any number that's not a perfect square, so not like the square root of 9, but take the square root of 8. You cannot write the square root of 8 as a fraction. It's impossible. And if you're thinking, well, maybe could we ever figure out maybe someday how to do it? No, I could prove to you that no matter what, we will never figure it out because it cannot be done. I could prove it. So any number that's a square root of something besides a perfect square, those are all irrational. And together, if you take all the numbers that you can't write as fractions and the ones you can, those are your real numbers. Okay? In Algebra 1, that's all you study. Okay? Now, somebody mentioned I. So I is kind of going beyond real numbers. Okay, we're not going to get to that just yet, but we will. And the reason we invent I, it's like, well, why would you want to have imaginary numbers? What's the point? Well, if I ask somebody to do this in Algebra 1, they write undefined. Well, if you're going to write undefined for that, it's only because you don't understand that there's other kinds of numbers that can give you an answer. It's kind of like writing undefined for 3 minus 3. If you know that there's a number that exists that can give you the answer, then you would write it. You just write undefined if you don't understand that there is something more that can give you the answer. And that's when we get into imaginaries. Okay? So we'll talk more about that kind of stuff much later on. But that's the whole point of inventing these new types of numbers, so we can deal with fractional pieces, deal with negatives, or even more complicated, deal with something like that. So any questions on the number set? Kind of where the numbers fit in? Another way you can look at the diagram is you could say if something is a counting number, it's automatically a whole number. Okay? If something is a counting number, it's also automatically an integer. But let's look at it the other way. If it's an integer, is it a counting number? Not always. You can kind of think of it as places. Think of the middle as the most specific. Okay, think of that as like Boston. Think of whole numbers as Massachusetts, United States, and then rational numbers as North America. If you're in Boston, you're automatically in Massachusetts. But if you're in Massachusetts, you're not automatically in Boston. Okay, so it doesn't work the other way. So when we talk about these number sets, what else did I have? Okay, this I kind of already told you. A rational number is a number you can write as a fraction. Okay, the top and the bottom of the fraction are both integers. So technically we don't, that's not a rational number. You might say, oh, it's a fraction. Yeah, but look at the top. The top and the bottom have to be integers. So does that mean you can't have a decimal in a fraction, like 1.3 over 2.4? It's not really the proper way to write a fraction. You'd write that as 13 over 24. Okay? That is not rational, even though it's a fraction. The top and the bottom have to be integers. And of course, the bottom can't be 0. We cannot divide by 0. Okay. Any questions on that? So I'm just going to show you some of the symbols that we use. Some of them, I think, they make sense where they kind of come from. Like this symbol that we have here, that's the symbol for real numbers. The symbol that we have for rational numbers kind of looks like a Q, but it has this extra line in it. Any thoughts where a Q would come from for rational numbers? Anybody think of a word that begins with Q that has something to do with rationals? Yeah? Quotient. So that's my best guess, maybe where the Q comes from. And then the Z for integers. I have no idea. So, but they use it. Okay, so that's just a short way. So if you see me write down one of those symbols, you know I'm talking about real numbers, integers, or rational numbers. What do you think something like this would mean? Like a Q with a plus. What do you think a Q with a little plus would mean? How about Renee?
Would there be positive integers?
I like the first part, positive rational number. So if you see a Q with a plus, that means we're talking about positive rational numbers. Okay, so you can put a plus or a minus if you want to indicate positive or negative. Okay, so in math, the 4 basic operations we deal with that are binary are add, subtract, multiply, and divide. So, what does that mean? Binary. You know what that means? Yeah.
They're kind of like the primary ones, the primary ones, the main ones.
So let's focus on the first part of that word. There's a prefix in there. What's the prefix? Yeah?
Bi.
Yeah, bi. Bifocals, binoculars, or you say binoculars. But bicycle, right? Bi, 2. So, 2 things. Anytime you want to add, subtract, multiply, or divide, you have to give someone 2 things. You can't say, add 7. What? Give me another number and I'll add 7 to it. So add 7 to 12. You need 2 things. So these all require 2 things to work. Something like a square root, that's not binary. Square root, you just give me 1 number. That's all I need, and I can take the square root. Okay, so we'll go over a few properties of addition, like commutative, associative, identity, things like that. So for the examples I'm about to give you, I'm going to use the letters A, B, and C. And A, B, and C can be any real number. Positive, negative, fraction, decimal. So closure. We kind of talked about this earlier. I didn't call it this, but that's what it is. If you take an integer plus an integer and get an integer, that means addition is closed under the set of integers. Because you can take 2 of the things, integers, combine them, and still get a number that's in the same set. Now, if we said something like subtraction, subtraction is not closed under counting numbers. What does that mean? You can take a counting number minus another counting number, and the answer is not a counting number. Okay, for something to be closed, you have to take something in the set, something else in the set, do something to it, and the answer is still in the same set as the 2 things you started with. Okay? Any question on what closure means? So addition is closed under real numbers. In fact, pretty much everything is closed. If you add real numbers, you get a real number. If you subtract real numbers, you get a real number. If you divide them, or if you multiply them, you always get a real number. Okay, so commutative. Commutative basically means we can switch the order. Right? A plus B, same as B plus A. How about associative? Commutative has to do with order. Does anybody remember what associative has to do with? Yeah?
A plus B equals B plus C? Or, wait, no, never mind.
Any other guess? Yeah?
Would it be like A plus B and B plus C equals A plus C?
I think maybe you're thinking kind of like of a transitive property. Like if A equals B and B equals C, then A equals C. Kind of, I'm not 100% sure, but maybe we are. I think we're going to talk about transitive. Maybe not today.
Has to do with the grouping.
Has to do with grouping. So with grouping, I need a third thing. So the order is the same on each side. ABC, ABC. The difference is on the left, I've grouped B and C together. I'm doing that first. And on the right, I've grouped A and B. So it just has to do with grouping, the order in which you do things. If you notice, all the properties I'm focusing on right now are for addition. Some of these do work for multiplication as well, and we'll talk about that a little bit. The identity property. So the identity property is basically what you can do to something and not change it. So for addition, what can you do to something and it will give you back the same thing you started with? Yep.
Add 0.
Add 0. That's not the same for multiplication. If you say, oh, if I multiply by 0, I get the same thing back. No. what would be the identity property for multiplication? What would you multiply by that never changes? 1. Yeah. 1. So the identity property, a little different for multiplication. It's more like A times 1 equals A. But commutative and associative are exactly the same. Just change the plus to a times. Inverse property. It's just basically what you can add to something to get 0. Okay, so for addition, it's what you can add to something to get 0. It's just the opposite. That's all. So anything plus its opposite is 0. And then distributive. Distributive, that's just the basic idea that you've got something in parentheses, something on the outside, and you can distribute it. Okay. How about if I had this? What's the difference between the end result if I did what's in black or what I just wrote in red? Yeah.
You solve what's in the parentheses first and then multiply it? Is that going to be different?
Well, if these were actual numbers, like if this was 2 plus 3 times 4, then yes, we could actually, we could do what's in the parentheses first. But let's pretend they're all letters. So since B and C aren't like terms, we can't actually add the B and the C. Just like we couldn't here. Yeah?
It wouldn't change.
Wouldn't change anything. That's exactly the same thing. In fact, what property did I use to get from this to this? It's one of the properties we...
Associative.
Grouping is the same. B and C are still grouped. Yep.
Commutative?
I use the commutative. If you think of this as 1, think of this as 2. In this case, it's 1 times 2. In that other case, I flipped it. 2 times 1. So it's basically commutative property for multiplication. That's all. Okay, so all those properties for multiplication are in your book on page 2. Okay, so we're not going to go through every single one of them again. There's no distributive property for multiplication. Distributive only works when you have addition or subtraction in parentheses. You would never distribute if you had something like this. You don't distribute there. If it's a plus, now you distribute. Commutative, I already told you, basically looks the same. A times B equals B times A. Identity property is a little different. A times 1 equals A. You don't use 0. Okay? But again, all those are on page 2 for multiplication. Okay, so an equation. An equation is when you basically take an equal sign and put it between two expressions. There's 3 types of equations, or one way to classify them into 3 different categories. And there's an example of each one on the board right there. 2x equals 12. That's an equation. 5 equals 2. It's definitely an equation because I put an equal sign between 2 expressions. And 3 plus 4 equals 2 plus 5. Okay, so all equations, 3 different types. Let's start with 5 equals 2. It's an equation. Any thoughts about that equation? 5 equals 2? Yep.
It's not true.
It's not true. That's a contradiction. So a contradiction is an equation that is never true. And sometimes when we solve equations, we end up with something just like that, which means there is no solution to it. Maybe you started with 2x plus 5 equals 2x plus 2. The 2x would cancel from each side, and all you'd end up with is that. How about this one? 3 plus 4 equals 2 plus 5. Thoughts about that equation, Robin?
7 equals 7.
7 equals 7? Okay. So, tell me about that. Yeah, it's true. And that's called, begins with an I. Does anybody remember what that's called? If you have a number equal to itself. Identity. Yep. Great. It's an identity. Now, this one is a little different. That's a conditional equation. What that means, 2x equals 12 could be true if you pick the right number for x. So that's a conditional equation. So could be true, identity, always true, contradiction, never true. Now I think we're going to get into the property that somebody mentioned earlier, like transitive, if A equals B and B equals C, A equals C. But to get into those properties, you have to have equal signs, which we just talked about. So 3 properties that are usually studied together: reflexive, symmetric, transitive. Okay. Anyone think they know what the first one means? Reflexive. If you get confused, kind of think about it. If you look into a mirror, compare what you see in the mirror to what is standing in front of the mirror. How do they compare? Yeah.
A equals A.
Yeah, basically it's like it's the same thing, right? Something equals itself. So that's reflexive. Symmetric is a little different. That's basically if A equals B and B equals A. So if A equals B, then B equals A. So if you write on a test x equals 2, and somebody else writes 2 equals x, same thing. And then transitive, I kind of already said that one. Transitive is when you have a chain of things. Okay? It can be 2 things, 3 things. Here's a chain of 2 things leading to a third conclusion. If A is equal to B, and B is equal to C, then A is equal to C. And that's used all the time. You can use it with parallel lines. If A is parallel to B, and B is parallel to C, then A is parallel to C. If you think of laying bricks, that's exactly the idea. As long as your first row is level, then any row you put on top of that, as long as you make sure that row is level, they'll all be level to each other. It's like transitive. All of them are parallel to the first one. All right, so not as concerned if you know how to solve this. I'm more just concerned with the steps and just making sure we can justify each step. Right, so the directions here basically say x can be any real number. Show that what's on the left is equal to what's on the right. It's kind of like a proof, except the reasons you're going to give me are all right here. You just have to do these 3 things out one step at a time. Okay. So, distributive property. Kathleen, do I have any distributive property on the right-hand side? No? How about on the left?
Not yet.
Can you tell me how to do just the just tell me what I would do for the distributive property on the left?
multiply 2 by x.
So 2 times x, okay.
And 2 times 3.
And 2 times 3. Now, normally I would just do that out, but they're having us kind of spell out each step here. So now we do that out, we get the simplified part, 2 times x, not really a lot we can do with that, 2 times 3. Okay, but what's on the left and what's on the right, they're not exactly the same, but we can switch them because of the commutative property. So all we have to do is switch those 2 things. So 6 plus 2x equals 6 plus 2x. So there's a couple ways you could see a problem like that on the test. The reasons could already be written for you like that, and you show me the steps, or I do it this way. I show you each step, starting from the original problem to the final answer, and you show me why can I go from this step to this step? What property did I use? And then you'd have to tell me distributive. Okay? How did I go from, this step to this step? Commutative. Okay, so you could see that kind of problem either way. Any questions on that? Right? So that's where you'd see these different reasons pop up. All right, coordinate system. We'll go through this real fast. So starting out with value in two-dimensional coordinate system, just one-dimensional, just a single number line. Positive numbers always go right, negatives left, origin right in the middle. So using a number line, now we can give an order to numbers. It lets us compare numbers. And there's 4 symbols we use to compare numbers, generally. And there's a name for them. Anybody know the name of the 4 symbols I'm thinking of? Well, what does that symbol mean? I know what it's called, but what does it mean? Yeah?
Equal to.
Equal to. It means equality. Okay. So if we're comparing two numbers that are not equal to, we're using this kind of symbol. Does that help?
Greater than, less than, greater than, equal to, less than, equal to.
Yep, those are the 4 symbols, and those are called your what symbols? They're not
Inequalities.
inequality symbols. Yeah. So those 4 symbols are inequality symbols. And again, if you already know the inequality symbols, you don't have to write these down. It's up to you. I'm just trying to remind you of what they are real quick, and that's it. Okay, because we're going to get to a little bit of calculator stuff today, so I think that's the part where that might be kind of new for people. Okay, any questions on the 4 inequality symbols? Okay. So when we're graphing on a number line, there's a couple different ways that we can show, like if, let's say you wanted to graph x is greater than 3. There's a certain kind of circle you can use for greater than and less than. And then there's a different circle you use when it has the equal to. Anybody know the 2 kinds of circles I'm talking about? Mm-hmm.
Like an open circle, closed circle.
Yeah, open circle or a closed circle. Now this is one way to do it. I'm going to show you another way besides open and closed circle that you're going to see in our book a little bit. Okay, but anytime you want to graph on a number line, you put an open or a closed circle on the number they want you to graph. And then we usually end up shading. Sometimes you shade left, sometimes you shade right, sometimes you shade between. Depends on the kind of problem. We'll try a couple right now. Okay, first thing I wrote, x is greater than or equal to 2, and then 2 is less than or equal to x. When I graph what's on the left and what's on the right, what's the difference? In terms of when I graph both of them, how are the 2 pictures going to compare to each other? About Ashton?
The arrows are going to go different ways.
The arrows are going to, and how come you think the arrows are going to go different ways?
Because one's greater than and equal to, and one's less than.
Okay, so you got one greater than pointing to the right, you got a less than pointing to the left. Okay, any other thoughts? Yeah.
Isn't it going to be the same thing? They're just mirrored image.
Gonna be
Because the 2's still going to be less than or equal to x.
Yeah.
Either way you read it.
right. That's really the same problem. The way that we write it on the left, that's the preferred way. Usually we put the variable on the left, and if you put the variable on the left, then the inequality indicates the direction to shade. If you put the variable on the right, this is actually telling you the opposite way to shade. Okay? But those are actually the exact same problem. Okay? Pointing towards the 2, it's still pointing at the 2. Okay? Any questions why those are the same? Same thing. All right, so let's graph it. First thing, let me just number it. It's good enough. There's lots, you can number it however you want, as long as 2's on there somewhere. So Gabe, what kind of circle would I need, and what number would I put it on?
Which game?
Oh, Gabe.
So we need a closed circle on 2.
Perfect. Closed circle on 2. And which way am I going to shade?
Right.
To the right. We want to shade everything that's greater than 2. So that's to the right. Okay, I know some teachers have you shade above the number line. I don't really care if you shade above it, on it. Anything like that is fine. Okay, let's take a look at this one. This is the same thing. What's on the left and what's on the right, there's no difference between them. I'm just showing you again. How about, Kaylee, which way do you think I would prefer you to write it? The way that's on the left or the way that's on the right?
On the right.
On the right, yeah. I'd like you to put the variable on the left side, put the number on the right side. Then you can always go by the inequality, and it tells you which way to shade. Okay, let's graph that one. So first, we'll put some numbers. You can skip numbers like that as long as you're, if I got to go by 3s, I would have to go by 3s everywhere. Can't all of a sudden do that. That doesn't make sense. You don't even have to number as far out as I did. -3 to 3 is fine. How about, Gabe, what kind of circle do I need here?
Open.
Open? What number?
3.
3? And shade which way?
Right or left?
Left. Yep. And that's it. Okay, questions on that? Okay. Let's see, does anybody know the other way to do this on a number line besides an open circle and a closed circle? There's another pair of symbols you can use. Okay, so what you're going to see in our book is brackets in place of a closed circle. And we're going to use brackets for a lot of other things. Anytime you have an equal to, think bracket, because that'll come up a lot. So in this problem, I think it's the same one we already did. Yep. The only difference is instead of putting a closed circle on 2, you put a bracket. But it requires you to know which way you're going to shade before you put the bracket, because you always have the bracket opening the direction you're going to shade. So we know we're going to shade right, so the bracket opens to the right. It's just a different way of doing it. That's all. Any question on doing it as a bracket? You should be comfortable with both. Circle, open circle, closed circle, bracket. Any thought what kind of symbol you're going to use when it's a less than or greater than? Besides the open circle. What do you think the other symbol we would use is besides a bracket? Any guess? How about Jark? Any guess? Jark? Sorry.
Like a parenthesis.
Yeah, a parenthesis. So when we have an open, when you have an open interval, like a greater than or less than, we can use a parenthesis. So let's graph the same one we just did. But just like a bracket, a parenthesis can open left or right, so you have to know beforehand which way you're going to shade. And Blake, which way am I going to shade this time? To the left. Yep. So parenthesis on 3, shade left. Just a different way. I don't really care if the directions don't specify how to use or which symbols to use. I don't care which symbols you use, but don't mix symbols. Just stick with whatever bracket or parenthesis or the circles for whatever problems you're doing. Just stick with the same symbols. Okay, so this is a little different. This is a compound inequality. Okay. Compound inequality involves it's either the word and or the word or. when you have a compound inequality like that, which word does that involve? And? Or is it or? Yeah, it's and. The way you read this is 2 is less than or equal to x, and x is less than or equal to 9. That's an and. Okay, and specifically, it's called a conjunction. So conjunction is when we have the word and. Now, if you want, you can take and break it apart into that. 2 is less than or equal to x, and x is less than or equal to 9. So you could write it out just like that. Here's what's in the black box. X is less than or equal to 9. And what's in the red box is right here, but remember we talked about how you can rewrite it. 2 is less than or equal to x, x is greater than or equal to 2. Same thing. So when I graph something like that, how do you think the shading is going to work? Shading on the last couple problems was kind of open-ended. It just kept going, either left or right forever. What's going to happen there? Yeah.
It's going to be between two closed brackets.
Yep. If you're doing brackets, it's going to be between two closed brackets, or it's going to be between two filled-in circles. Okay, so let's graph that. All right, so we have to go from 2 to 9, so let's just go. That's fine. And Chris, do you want to use the circles or the brackets? Brackets. So we're going to put a bracket on 2 facing which way?
Facing towards, like going up, greater.
Yep. So I'll have that one facing right. And how about the bracket on 9?
Facing left.
Facing left. And he just said earlier, shade between. Any questions on that? Okay. Absolute value. What is absolute value? Anyone define for me what that is? Yeah.
How far away it is from 0.
Exactly. If you want to think of it geometrically, the easiest way to think of it is how far a number is from 0. Now, I want to think about it a little more formally. I want to think about it in a way that if I was going to program a computer, say somebody types a number in, they hit enter, and the computer wants to give back the absolute value of the number. Okay? There's really 2 cases I would have to think about. Depends on what kind of number they put into the computer, whether or not I have to do something to it. Does anybody have an idea of what the 2 cases might be? Depending on what somebody would type in. Yeah?
Isn't it if it's a positive number, then that's just the absolute value, but then if it's a negative, you have to take the negative sign?
Okay, so we have to deal with whether it's positive, whether it's negative, and we also left something out. What else is there besides positive and negative? Zero. So we also have to think about that. And 0, we could just kind of lump in either category. It doesn't really matter. So what happens if you type in a positive number? What should the computer do to it to get the absolute value? Yeah, nothing. So if you type in a positive number or even 0, the absolute value of that number is just whatever you typed in. It's the same thing. But what if you type in a negative number? What would the computer have to do to it to give you the absolute value? So if a was less than 0, yeah? And how do you do that mathematically? Take away a negative sign. Yeah?
Multiply by negative.
Yeah, multiply by -1. So to find the absolute value of whatever you type in, if you type in something less than 0, take the opposite of what you typed in. So if I had the number -8, -8, if this is case 1 and this is case 2. -8 falls into this category. So it says, okay, the rule is if you're less than 0, which we are, take the opposite of the number inside the bracket. Well, the number inside the bracket is -8. The opposite of it, +8. So that's formally how you define absolute value. Okay? If it's positive, you don't do anything, or if it's 0. If it's negative, you take the opposite. So real quick, we'll just go through that. Absolute value of 6 would be 6, -3. Okay. All right. Distance between 2 points on a number line. What operation would you use if I said, here's a point, tell me how far apart they are? Subtraction. And specifically, distance has to be what kind of number? Yep.
Positive.
It's got to be positive. So in order to make sure something is always positive, that's why we use absolute values. So if you've got 2 points on a number line, you want to know how far apart they are, just subtract them and make sure the answer is always positive. Okay, so let's set that up. Find the distance between -2 and -9. Madison, could you set up just the expression for me, and then we'll go through the answer together?
Want to just be like the absolute value.
Yep.
Like -2 -9.
And then minus what?
-9.
Minus -9. Yep. Okay, so we got the absolute value of -2 minus -9. What's going to happen?
Cancel out.
What cancels out?
The negative.
Yeah, the -9. So minus a -9 turns into a +9. And now -2 plus 9 gives me 7. And the absolute value of 7? 7. Okay. Now, if you switch A and B, like here, if we switch -2 and -9, would that make a difference in our answer? See, some people say no, but I thought when you subtract, the order matters. 5 minus 2, 2 minus 5. It's not the same thing. Yeah?
It's because the absolute value
Right.
changes.
The absolute value is going to basically make it positive. So in this sense, if you switch A and B, it doesn't matter. All right, so we'll go through two-dimensional graphing real quick. Just kind of all the important terms. And if you know these, you don't have to write. So now we're going from having a number line just on one axis now to 2. So the horizontal number line is your x-axis, vertical is your y-axis. If we're going to do it in 3D, does anybody know what other axis we would have?
Z.
Z. Yeah, we'll do 3D stuff later on. Whenever you add in an axis, it basically doubles the amount of regions you have. When you have just a single number line, you have everything to the right of 0 and to the left of 0. It's basically 2 regions, positive, negative. Well, now with 2 axes, we have 4 regions, and we call them regions 1, 2, 3, and 4. Then anybody know what we call those 4 regions? We use a better word. Quadrants. Kind of continuing that idea, if you added another axis, you would double the number of regions again and have 8, and we would call those octants. And then beyond that, now we're in like 4 dimensions and more than we can visualize. Okay, so we have our 4 regions. On the x-axis, positive is right, negative is left. On the y-axis, positive is up, negative is down. And I've tried to show that with the parentheses and the plus and minus sign. Where the 2 axes intersect is the origin. I think that covers most of the basic vocab stuff, two-dimensional graphing. Questions on that? Okay. So, XY written like that, that's called a coordinate. Or if you want to be more specific about the kind of coordinate, it is an ordered pair. 1, 2. It's a pair. Something like this, that's still a coordinate, but it's not an ordered pair. Does anybody know what you would call x comma y comma z? Yes, it's an ordered triple. Okay, so ordered triple. So if you say, oh, I have a coordinate, that's pretty vague. It could be 2D, could be 3D, could be 4D. But if you say I have an ordered pair, I know, okay, you're talking x, y dot. All right, so zooming on a graphing calculator. All right, so a lot of times when we do things on the calculator, we might type something in, especially a graph, and we can't see it. And it could be off the screen. So it takes a little bit of practice to get used to just learning how to zoom. So what I'm going to do is maybe turn the calculator on. Okay, press on. And I want you to type in y equals x. Well, actually, let me start nice and slow. Press the y equals button. Okay, that's up at the top. And now you should see the screen. And on the first line, if there's anything there, you can just hit clear, and that should get rid of it. And I want you to type in x. X is the button right below mode. And then the squared button is on the left-hand side, 5 buttons down. I want you to type in x squared plus, and then put 12. When you graph x squared, what kind of shape is that? It's not like y equals mx plus b. That's not a line. What does x squared look like? It's a parabola. And the plus 12 is going to shift it up 12. What I want you to do is press window. Actually, we'll come back to window. For now, press zoom. Now, before you press anything else, just watch me. If you press zoom 6, but hold on 1 second, what's going to happen is it's going to change the x min and max, which is how far left and right you see, the y min and max, which is how far up and down you see, to these values, -10 to 10. Mine's already set, but in case yours isn't, go to zoom and press 6. And if we look at it, the little yellow in the upper right-hand circle thing that was spinning, that tells you the calculator is doing something. Mine's done now, but I don't see anything. I don't see anything because I purposely gave you a parabola shifted up 12 units. You're only looking as high as 10. So what we're going to do is we're going to change the window. We're going to look a little higher than 12. Now, really, there's only one number we need to change. Okay, I'm going to have you practice changing all 4. All you would have to change is y max. If you look higher, you'll see the parabola. You don't need to look further left, you don't need to look further right, but we'll practice typing it in. So when you see a window like that, the order of the numbers is the following. First 2 is always your x-axis, min and max. Second 2 is always your y-axis, min, max. So we're just basically typing in -20 to 20. If you switch the 20 and the -20, you'll get an error. You can't have the max be smaller than the min. It just doesn't work. Now, if you type -20 and just hit enter, 20, or use the down arrow, either way. -20 and 20. So now if I hit graph, I should definitely see my parabola. There it is. It has a vertex at 0, 12, and it goes up from there. Now, I didn't talk about a couple other things in the window, like the X scale and the Y scale. That's how often you see tick marks on the screen. It's not really that important. If you want to put a tick mark every 5 units on the x-axis, you could change the scale to 5. It does nothing to the picture. It just changed the markings on the axis. That's all. I don't usually ever play with the x and the y scale. I don't really see a need to. And that's pretty good. Okay. If, let's say you want to look at some points along the curve, you can press trace, and it's telling me 0, 12 is a point on the parabola. As I trace, it's giving me all different points. 2.1, 16.5. Those are all just different points on the parabola. I think if you press trace, you can even plug in an exact number. Like, let's say we plugged in 1. So we plugged in, we did what? Y equals x squared plus 12. So 1 squared plus 12 is 13. So if I plug in 1 and hit enter, it tells me y is 13. So that's another point, another coordinate on the parabola. Any questions about changing the window? How to do that? There's lots of other ways you can change the window. I can do zoom out. So if I do zoom 3 and put my cursor kind of around the area that I want to zoom out, it'll zoom out. But if you zoom out too much, now you're starting to distort the parabola. You're starting to make it look really long and skinny. And if you keep zooming out, eventually you're probably not even going to be able to tell it's a parabola anymore if you zoom out enough. Well, certain features I've definitely lost. To me, it almost looks like in my calculator the parabola is coming from the origin, because I've zoomed out so far I can't even tell. So sometimes zooming out far is a good idea to get a big picture, but sometimes to see like detail, you need to zoom in more. And as I zoom in and out, see how it changed my mins and maxes? They're not negative 20 to 20 anymore. So the scale on the calculator, I already talked to you about that. That's just the tick marks. It's not really important. And actually, I already answered that question too. If you change the scale to 5, which is exactly what I did, it puts a tick mark every 5 units. Questions on that? Yeah. Zoom in and out. So let's say I want to zoom back in now, because I want to see where the vertex is for that parabola. I'm going to press zoom. I'm going to press 2. And then I get a little cursor that's blinking. Wherever I put the cursor, that's where it's going to zoom into after I hit enter. So I'm going to try to put it what I think is near the vertex. I'm going to hit enter. And it's a little hard to tell, but it did zoom in. Okay, I'll do it one more time. Zoom. I pressed the wrong thing. So I press zoom. 2. I'm going to put the cursor kind of towards the area I want to zoom in. It's a lot easier on a calculator. You just hold it. Mine, I can't do that. Now you can also see the tick marks getting more defined. They don't look all squished together because I'm starting to zoom back in. Did that work? No? So we did 1, 2, and then we hit enter. And now we'll zoom in. So once you zoom in enough, eventually it's gonna go off the screen again. All right, distance formula. So I think that'll. Yeah. So distance formula on a number line, pretty straightforward. When we have distance formula in 2D, it's a little different. So if you get something like this. I want to know the distance from here to here. How could I I find the distance between those two dots? What could I do? Pretending like I don't have a ruler or anything like that. So I can't use a ruler. I want to do something like a calculation to find the distance between the two. Yeah?
You can make a right triangle used Pythagorean.
Exactly. That's all the distance formula is. So basically means you're making a right triangle. The other two distances, I don't need a ruler. Those are simple. I can just count. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. And now I basically know two sides of a right triangle. I can use Pythagorean theorem. Okay, so that's basically the distance formula. So if you have your coordinates x1, y1, and x2, y2, let's label mine that way. Let's just take this, just move it down there. So that point is x1, y1, and that point is x2, y2. I need to just figure out how long each side is. Now, when it was on a grid, you could just count, but let's pretend it's not on a grid. How would I figure out how long this bottom side is? There's a calculation I could do with the labels that are up there. On that way, let me see what we could do to find the length of that bottom side.
You could do something like the midpoint thing.
You're not going to need midpoint, so you won't need the midpoint to do it. It's just, think about whenever you want to find distance between 2 points, what operation do we use? And we did this with the number line. Yep. Yeah, we're going to use subtraction. So the question is, what two things would you subtract to find the length of the bottom side? Yeah,
The
Gabe?
x values.
The x values, exactly. Just take x2 minus x1, and that's the length of the bottom side. This point is at x1 on the x-axis. This point is at x2 on the x-axis. Subtract them. There's the length of the bottom. How would we find the height? What would be my calculation to find the height of the triangle? Yeah.
Y2 minus Y1.
Yeah, we just do y2 minus y1. So y2 minus y1, x2 minus x1. There's the two sides of the triangle. We just fill them into the Pythagorean theorem. So we take, whether you do x2 minus x1 or x1 minus x2, it doesn't matter because you're squaring it. So length of the bottom squared plus the other leg squared, add them up and take the square root. That's just your Pythagorean theorem. Okay, so to find the distance, it doesn't really matter which one is x1 and which one is x2. Doesn't matter which one is y1 and y2. Just be consistent when you set it up. So Tori, could you set up my distance formula for me to find the distance between 1, 4 and 5, 6?
Yeah, the open parentheses 1 minus 5 close parentheses squared plus open parentheses 4 minus 6 close parentheses squared.
And when we do that out, we're going to get 1 minus 5 is negative 4. Squared is 16. 4 minus 6 is negative 2. Squared is 4. And I get the square root of 20. But how can I simplify the square root of 20? There's a way I can reduce it. Yeah?
4 times 5 and the square root of 4 is a perfect square, so it'd be 2 root 5.
Yep, exactly. So anytime you have a root that can be reduced, I always expect you to make sure you reduce that as much as you can. Okay, so there's distance formula, which kind of covers how to reduce square roots. And the last thing is midpoint formula. So somebody mentioned this formula earlier. Midpoint, kind of usually in textbooks they go together, midpoint and distance. I think midpoint's a little easier because you don't have to do square roots. Okay. If you look at the midpoint, what are you really doing? Like right here. x1 plus x2 divided by 2. There's a name for that calculation. Yeah,
Isn't it just finding the average?
it's just the average. If you add two things up and divide by 2, all you did was find the average. So basically you're averaging the x's and you're averaging the y's. That's the midpoint formula. Okay, so the last one, we'll find the midpoint between those two numbers. Okay, and when I think midpoint, I don't even think of the formula. I just think, okay, I'll just average the x's, average the y's. Just find what's in the middle. So if we take -5 plus 3 and divide by 2, we get -1. And 2 plus 7 divided by 2. Yeah, 4.5, or if they don't care, you can just leave it as a fraction. 9/2. Okay, so any questions on that? Again, that's a lot of different stuff. Distance, midpoint, graphing, inequality symbols, all the properties. But hopefully most of it you already were familiar with. Okay, homework tonight, it's on page 11. It's 1 through 16, 20 to 23, 30 to 32, 38 and 44. Again, I'll post this online, so if there's anything you need to double check, you know the website, you can check it. And the other thing I wanted to mention about the website is if you go on and you subscribe to Math with Hager, I'll give you 5 bonus points on the next test. Okay, so if you go on and subscribe before the next test, which is until next academic week, I'll give you 5 bonus points.